Welcome to this third and last video in our smooth muscle lesson. In the first two videos we covered some general aspects of smooth muscle, how to categorize it, how it works, and we covered the excitation, contraction, coupling process in some detail. So now what I want to do is present arteriolar smooth muscle as a typical example of how smooth muscle works. So just a quick review. We talked about excitation, contraction, coupling in smooth muscle. It's quite different from cardiac muscle. We start with either electrical excitation, that is a change in membrane voltage, which will typically open or close voltage-gated calcium channels, or pharmacomechanical coupling, the way that the autonomic nervous system works, a very good example of how that can happen. Okay? Either way, that causes calcium to enter across the surface membrane or be released from the SR in the case of certainly electrical excitation and some forms of pharmacological pharmacomechanical coupling. This is not necessary for all forms. Remember, we went through the action of the beta receptor where the action was entirely on the level of myosin light chain kinase. You didn't need a change in calcium to get that to work. But nevertheless, you can, certainly you should know, any increase in calcium will increase the force of contraction in smooth muscle. And then we have increased phosphorylation of myosin through myosin light chain kinase. Calcium binds to calmodulin. Calcium calmodulin activates myosin light chain kinase, and that phosphorylates the myosin. Okay, so in the classical excitation, contraction, coupling process, that starting with calcium, we should think about that happening. And then phosphorylated myosin binds to the actin, and we get cross-bridge cycling and generation of force, and that'll continue as long as calcium and ATP are present. Okay? So that's how excitation, contraction, coupling generally works. Of course, our receptors will feed into that process at in various ways, okay, and have various effects depending upon how they feed into it. And the autonomic nervous system was a great example of that. So having said that, let's talk about arteriolar smooth muscle. This is arteriole. This is an arteriole here, and basically, the purpose of arteriolar smooth muscle is to change the resistance to flow locally. So what you're doing, the arterioles are changing sort of gatekeepers. They're stopcocks that allow blood to access different capillary beds in your tissues here. Okay, and depending upon how contracted those arterioles are, you will have a distribution of blood that will vary to these various different tissues. The more contracted the arteriolar smooth muscle is, the higher the resistance to flow, and the less blood will enter the tissue, the capillary beds in the tissue. The more relaxed that smooth muscle is, the bigger the radius of the arterioles, the more flow of blood that you get, and the more flow you get to the capillary beds in each of these tissues. Okay? So arteriolar smooth muscle is activated by the sympathetic nerves only. There's no parasympathetic nervous system innervation, with exceptions. They're rare exceptions. The innervation to the arteriolar smooth muscle, for instance, in the male genitalia, there are areas which are actually innervated by the parasympathetic nervous system, and we'll worry about that a lot more when we get to the sexuality and reproduction block. But for right now, know that blood flows to each of these tissues. The arteriolar smooth muscle is the gatekeeper, and the more the resistance to flow, the less blood the capillary beds in these tissues gets. Okay? Arteriolar smooth muscle controlled by extrinsic factors, which are neurological and hormonal. In the case of nerves, we're really talking about sympathetic nerves. and also by local controls, okay? And those are mostly local metabolism, depending on local metabolism. Local control, most important to matching blood flow to metabolic need. So this is the typical amount of the cardiac output that each of these organ systems will get. And for instance, if I increase the activity in skeletal muscle, if I start exercising, then obviously I'm going to want to increase the flow to the skeletal muscle so that skeletal muscle will get more oxygen and more nutrients. And so what you'll find out is that the metabolites build in the skeletal muscle, and that those local metabolites cause a vasodilatory response so that you'll get more blood flow. So your blood flow will more closely match the metabolism in the tissue. More metabolism, more flow; less metabolism, less flow. Okay. The extrinsic factors are mostly what you get in order to regulate mean arterial pressure. Okay, and so if your mean arterial pressure falls, your sympathetic tone will go up, and that will cause a constriction of many of the arterioles in many of the beds that you see here, though not all of them. For instance, you won't want a vasoconstriction to your heart, nevertheless, you will get a vasoconstriction to a wide variety of these, and a wide variety of these tissues. And the more vasoconstriction you get, the more resistance to flow there is in the system itself. So more total peripheral resistance means more mean arterial pressure. Mean arterial pressure is equal to cardiac output times total peripheral resistance. Increased total peripheral resistance from constriction of the arterioles in many of these beds means more mean arterial pressure, and your mean arterial pressure gets up closer to normal, okay, in the face of a fall. Okay. So local factors, all of these except histamine that I'm going to mention are related to changes in metabolic rate, and do note that these local factors, particularly the ones associated with the metabolic rate, do dominate over extrinsic factors. So your sympathetic tone will go up in exercise, but because your skeletal muscle is demanding more blood, because the metabolic rate is increased, you will get dilation in your skeletal muscle, not constriction. Okay, so the local response dominates over the extrinsic response, which otherwise might try to cause constriction to increase mean arterial pressure. Okay, so local factors dominate, bear that in mind, over extrinsic factors as a general rule. Okay. These local factors include decreased oxygen, more metabolism, less oxygen in the tissue because the tissue is eating it up. More CO2 is generated, so that'll cause each of these will cause a arteriolar dilation, a relaxation of the smooth muscle. Decreased oxygen, increased carbon dioxide, increased extracellular potassium, which you will frequently find in an active tissue. Increased acid, meaning a decreased pH, will cause a relaxation of smooth muscle. Increased osmolarity you will frequently find in active skeletal muscle in particular. And increased adenosine, which is a metabolite of ATP. So as phosphate is cleaved off of ATP, you generate adenosine, and that is a vasodilator. All these will increase blood flow in response to an increase in local metabolism. Okay, and these are local factors. Histamine also causes a local vasodilation through what is, for lack of a better way to put it, for me, an allergic response. Of course, this is not a response necessarily to local metabolic changes, but it is a local vasodilatory response. It's released when tissues are injured or in allergic reactions, and it causes vasodilation. Okay. Local influences also include heat, which causes a local vasodilation. We'll talk about that in a later lesson. Cold causes a local vasoconstriction. We'll talk about that in a later lesson, and why that is and how that integrates with the thermogenic response, or the thermoregulatory response, excuse me. And then the myogenic response to stretch, which we've covered in an earlier lesson, also a local physical influence, where the more you stretch the smooth muscle itself, the more the smooth muscle itself wants to contract against that stretch, and so you actually get a constriction. That's the myogenic response. It's largely behind what we called the autoregulatory response, which is particularly strong in kidney, although it's qualitatively present everywhere. It's much weaker in other tissues than it is in the kidney. Okay. Extrinsic factors: increased sympathetic activity will cause a vasoconstriction. Decreased sympathetic activity, you get a vasodilation. Okay, and hormones. Well, epinephrine from the adrenal medulla. Norepinephrine, not so much. Really, that's more from, you should think of that coming more from nerve endings in the sympathetic nervous system. These bind to alpha and beta receptors, which will cause our arteriolar constriction or dilation, depending upon which dominate. Typically, the alpha will dominate, and typically the response to norepinephrine and epinephrine will be a constriction. We'll worry about that more in the autonomic nervous system lesson. Vasopressin, angiotensin, both vasoconstrictors, both we will talk about at various times in this block, but really we'll get into the nitty-gritty of it with the renal portions of the vital fluids. So that is the end of this video and the end of this lesson. Thank you for your attention, and I will see you guys in the rooms.